Okay, so our next section here is section 10.7 on what's called parametric equations. So if it seems like we're jumping around a little bit, we kind of are. We're just finishing all the sections that the calculus teachers want you to see before you get there. Okay, so parametric equations turn up very often in physics. So what happens is, so far in our math career, if we've had an equation in two variables, we usually have an equation in terms of x and y. Now what we're going to have is we'll have equations with a third variable t. And why is our third variable t? Maybe you can guess this. I already told you guys this is going to come up in physics quite often. T for time. Okay, so for example, if we throw a ball, the ball has two different directions of movements, right? If I throw a ball, it has an up and a down movement, and then it also has a left to right or a forward backward movement. So this is a good example of something that can be modeled by a parametric equation. So we'll have this third variable t, and then what we'll do is we'll put x in terms of t. So on this throwing the ball example, we would measure the distance forward traveled by a ball as a function of time. And then y in terms of t. On my ball example, this would be the height of the ball as a function of time, okay? So, and it doesn't necessarily have to be time, but that's one of the common ones we see, which is why we have t for that third parametric, for the parameter. Okay, so I'm gonna write down our formal math definition here with some new terms, and then we'll do some examples and we'll work through this. So let x equals f of t. So x is a function of t. And y equal g of t. So y is a function of t. Where f and g are two functions with a common domain. The collection of points x comma y, which is f of t comma g of t, is called a plane curve. The equations x is equal to f of t and y is equal to g of t are called parametric equations. And t is called the parameter. Okay, so let x equals f of t and y equals g of t, where f and g are two functions with a common domain. So domain means what we can put into the function. So here our variable going into these two functions. So our variable going in is the t. So our common domain is going to be in terms of t. The collection of points x comma y, which is f of t comma g of t, is called a plane curve. And then those equations are called parametric equations, and t is called the parameter. All right, so what we'll do is 1, 2, 3, I think I have 4 examples of doing some parametric equations. We'll graph them, and we'll look at the corresponding rectangular equations in those domains. So first one, let's graph x is equal to t plus 4, y is equal to square root of t, and t is greater than or equal to 0. Okay, so this is a set of parametric equations. So here we have x in terms of t, here we have y in terms of t, and then this is our common domain. This is saying that t has to be greater than or equal to 0. And keep in mind that when you see these in physics classes, if t does happen to be time, usually we only measure time from 0 on. Usually we don't measure negative time. Like if I did that throw in a ball example, I wouldn't throw a ball and ask you what happened at a negative time because the movement didn't even start until time 0. Okay, so what we want to do is anytime we want to graph something, we have no idea what it looks like, we always can make a chart of values. But now we have 3 variables. We have our variable t. We are told that t has to be greater than or equal to 0. So for t, I'm going to start 0, 1, 2, 3, 4. And if you want to put ... here to remind yourself that this continues, you certainly can do that. Now what I'm going to do is in my chart of values, I'm going to make a chart for x values and y values. So first let's do x. So x is equal to t plus 4. So when t is 0, that makes x 4. When t is 1, x is 5. When t is 2, x is 6, 7, 8, and I'll put ... to remind myself this continues only in this direction. For y is equal to the square root of t. So square root of 0 is 0. Square root of 1 is 1. Square root of 2. Square root of 3. Square root of 4 is 2, and then ... So now these values of t helped us come up with these values of x and y. But what we're going to do is graph only by plotting these x and these y values, just like we have previously. Okay, so this parameter t helps us come up with these x and these y values, but we aren't actually going to plot t on our xy axis. So t is just used to get those x and y values. All right. So we see y going from 0 up to 2. So let me put some of these on here, 2, 3. And x goes from 4 to 8. So 1, 2, 3, 4. All right, so we're only plotting x and y. So the first point on our graph is 4, 0. The second point on our graph is 5, 1. The third point on our graph is 6, root 2, which is about 1.41. Then we have 7, root 3, which is about 1.71. And then we have 8, 2. Now you can see what's happening is that this curve is flattening out a little bit and is not a line, it's actually a curve. Looks like a square root function. Now look at the end of my plane curve here. Here I have an arrow, right? If we were to continue out, we'd get 9 and then, right, then we'd have square root of 5. And so these values continue in this direction. On this end of the graph, however, I have a solid end point. We do not have any values past this way because our graph only started when t was 0. So this is where our graph starts, our plane curve starts, and then this arrow indicates it continues out. The other thing you sometimes see on these plane curves is little additional arrows to show the direction of movement. So as t goes from 0 to 1 to 2 to 3 to 4, we've moved in this direction. So sometimes you see little arrows on there to show you that as t increases, this is the direction of our plane curve. Okay, the next thing we'll be asked to do is to come up with our corresponding rectangular equation. So as you saw in chapter 9, anytime we hear the term rectangular, that means in terms of x and y only. And so for this one, we had x, y, and t in those parametric equations. So we want to come up with the equation in terms of x and y only with no t. So our two equations were x is equal to t plus 4 and y is equal to the square root of t. Right, so what we want to do is come up with a rectangular equation, eliminate t. So what I'm going to do is I'm going to solve this equation for t, and then I'm going to plug it into the second equation. So I subtract 4 from both sides, I get x minus 4 is equal to t. What I'm going to do now is plug this in right here. So I get y is equal to the square root, and we got that t was x minus 4. So our rectangular equation is y is equal to the square root of x minus 4. Now, if you go back to what we learned in Math 126, we know that this indeed looks like a square root function, and the minus 4 shifts our graph 4 to the right. So this is just a square root function shifted 4 to the right. Now, you might be thinking, well, why don't I do this first and then just graph this and not make the chart of values? I would caution you on this. They should match up at some point, but sometimes if you only take this rectangular equation, the rectangular equation contains more points than the plane curve. So it's important that you actually go through this step of the chart of values to make sure that you get the graph correct. Sometimes this has more points than the plane curve. The next thing we want to do is find the domain of the rectangular equation. So our rectangular equation, the input here is x. So what we do is we take the domain of the parametric equations, which the problem gave us was that t had to be greater than or equal to 0. And we had that t was equal to x minus 4, so I'm going to plug this in right there for t. So x has to be greater than or equal to 4. Now, if we look at our graph, this looks correct, right? We could actually find this visually instead of algebraically. Domain refers to the x values on which our function is defined. And if we look at this picture, our function only starts, our plane curve only starts when x is 4 and is defined for everything after 4. So we could have picked this off of our graph without doing it algebraically. Any questions on this one? Okay, let's do another one. Let's graph x is equal to t squared plus 3, and y is equal to t squared minus 7. And t can be anything from negative infinity to positive infinity. Okay, so before you graph this, I would challenge you to take a look at these two equations and to think about what might your graph look like? What might your graph look like? Sometimes they're not obvious at all. So what we want to do when we don't know what something looks like is make a chart of values. So I'm going to make a column for t, and then we'll have x and y that are in terms of t. So t can be anything from negative infinity to positive infinity. So it's usually helpful to pick a few values around 0. So I'm going to put dot, dot, dot here to remind myself it continues. So I'm going to pick negative 3, negative 2, negative 1, 0, 1, 2, 3, and I'll put dot, dot, dot. So what I'm going to do now is fill in my x value. So when t is negative 3, x is 9 plus 3, which is 12. When t is negative 2, x is 4 plus 3, which is 7. When t is negative 1, I have 4. When t is 0, I have 3. When t is 1, I get 4, 7, 12. And again, if you want to remind yourself with the dots that this continues, you certainly can do that. Next thing I want to do is fill in my values for y. So when t is negative 3, I'd get 9 minus 7, that's 2. When t is negative 2, 4 minus 7, that's negative 3. Then negative 6, negative 7, negative 6, negative 3, and 2. All right, so next up, what we want to do is put all these points onto your xy axis and see what our plane curve looks like. So our x values range from 3 to 12, and our y values range from 2 to negative 7. So I want to make sure I get all of that on my graph. And then let's see, our x values go up to 12. So okay, so all we're doing is plotting these xy points. Remember, t helps us get x and y. We're not actually plotting t. So our first point is 12, 2. So here's 12, 2. Our next point is 7, -3. Then we have 4, -6. Then we have 3, -7. Now look at what's happened. We had 12, 2, 7, -3, 4, -6, 3, 7. Then our points go 4, -6, 7, -3, and 12, 2. So our plane curve, if it had a direction of movement, it went down like this. It stopped at this point and then turned around, and our values continue. So we actually just get, this should be a straight line here that ends at this point. I put an arrow on this end to indicate that if we looked at larger or smaller values of t, we would get points over here, but we never get a point past this point, right? When t is 0, that's our stopping point, and we turn around. Sometimes you see little arrows on this to show direction of movement. This one's a little bit tough because first we moved this way, then we stopped and turned around and moved this way. So we wouldn't usually put arrows on that because it's not very instructive which direction we're going. But this might be something like a pendulum or a spring where we move in one direction, have an abrupt stopping point, and then go back in the other direction. Any questions so far? Okay. So the next thing we'll do is we'll find the rectangular equation. So to find the rectangular equation, we want to put that in terms of x and y only with no t. So our equations were x is equal to t squared plus 3 and y is equal to t squared minus 7. So what I'm going to do here is solve this equation for t squared, and then I'm going to drop that in right here. So if I subtract 3 from both sides, I get x minus 3 is equal to t squared. So now I'm going to plug that in right here for t squared. So I get y is equal to, t squared was x minus 3. So we get y is equal to x minus 10 for our rectangular equation. Now let's look at this graph. Y is equal to x minus 10. Y is equal to x minus 10 would be this whole line, but it would also continue this way infinitely. So I would caution you, if you skip this chart of values and jump forward to y is equal to x minus 10, if you were to draw y is equal to x minus 10, it's going to actually contain all of these additional points. These orange points are in the rectangular equation, but not in the parametric plane curve there. Okay, so sometimes the rectangular equation contains more points than the plane curve. So be careful there. If you want to find the domain here, the domain of the rectangular equation. Okay, so the domain refers to the x values on which our function is defined. The algebra of this is a little bit not precise. The domain of our original parametric equations up here was that t had to be between negative infinity and positive infinity. So if we made a substitution for t based on these equations, right, solving for t here, we'd have plus or minus square root of x minus 3. So plugging in plus or minus square root of x minus 3 doesn't really work. So what we want to do is find the domain visually. The domain refers to the x values on which this function is defined. So this one, where does our function start? At what x value? 3. And then our function is defined for everything greater than 3. So we would just have that the domain is that x has to be greater than or equal to 3. And again, we find this visually from our graph rather than trying to plug in plus or minus square root in here, which doesn't really make a whole lot of sense. Okay, so anytime you hear domain of the rectangular equation, this is going to be in terms of x. Up here, the domain of our parametric equations was in terms of t. Okay, so domain of our rectangular equation should always be in terms of x. In terms of x. Any questions on this one? Okay, we'll do a couple more. Oh, the other thing on this one that maybe is a little bit interesting is that our original parametric equations, these were both quadratic expressions, but our plane curve actually ended up being a flat line. Whereas on this one, we had a square root and a linear, and we ended up with a square root. Okay, so sometimes it's not super obvious what the plane curve is going to look like. So let's do, I got two more for you guys. Next one, let's graph x is equal to 4t squared and y is equal to t plus 6. And our domain for t is that t goes from negative infinity to positive infinity. Okay, so again, we'll make a chart of values. So because t can be anything from negative infinity to positive infinity, I think it's helpful to pick things around 0 to get an idea of what this graph looks like. Then we'll fill in our x values and our y values. So x is equal to 4t squared. So when t is negative 3, that'd be 4 times 9, which is 36. When t is negative 2, we'd have 4 times 4, which is 16. We'd get 4, 0, 4, 16, 36. Y is equal to t plus 6. All I'm going to do is take these numbers and add 6. Okay, next step is we'll graph this. And remember, we're graphing the ordered pairs x comma y. We're not actually graphing t. T helped us come up with those x and y values. So let's see, our y values go from 3 to 9. So I want to make sure I get from 3 to 9 on my y-axis here. And my x values go from 0 to 36. So that's a pretty big range. So I'm going to count by 5s here. All right, again, we're plotting the x and y. So first we have x is 36 and y is 3. Then we have x is 16 and y is 4. We have x is 4, y is 5. And we have x is 0 and y is 6. Then look at what happens. These x values repeat, but these y values continue to go up. So we have 4, 7. Then we have 16, 8. And then we have 36, 9. I'm going to turn my paper sideways for a second to draw this graph in. So what we actually end up with is a sideways parabola, Now you've noticed I put arrows on both of these ends. So if we were to continue plugging in smaller t values, our values would continue over here. And if we plug in larger t values, our values would continue over here. These points follow one direction of movement. So you might see little arrows here indicating that as t increases, our plane curve moves in this direction. Okay, so we actually get a sideways parabola. The next thing we'd want to do is come up with the rectangular equation. So the rectangular equation is, of course, in terms of x and y and not t. So let's put down our two equations. We had x is equal to 4t squared and y is equal to t plus 6. Now this one's going to look a little bit different than the last two. So looking at this graph, we know that this graph is not a function, right? In order for something to be a function, it has to pass the vertical line test. Normally when something is a function, we put it in y is equal to form, but because this is not a function, that's not really a requirement. So looking at these two equations, the last couple of examples we solved for t from this x equation. If we solve for t here, we're going to get plus or minus square root something, which is really messy. So instead of solving for t here, I'm going to solve for t here. Subtract 6 from both sides, that gives me y minus 6 is equal to t. I'm going to plug that in right there. Okay, so that gives me x is equal to 4 times t, which is y minus 6 squared. We're going to stop right there. If you get something that's not a function, right, this is not a function, it's not a requirement to put it y is equal to form. Now this should look similar to the quadratic equations we saw in Math 126 in Chapter 3. And it does, the variables have just kind of switched places, which is why we have kind of a sideways parabola here. So you can stop right here, and on your homework, if you have a question like this, you don't have to continue to solve it. Now, the last two questions, we were asked what's the domain of the rectangular equation. We cannot talk about domain. Domain is a term that is only for functions. This is not a function. So you might be asked different questions on your homework. This asks, for what values of y is the curve defined? So there's two ways of doing this. The first is algebraically, the second is graphically, looking at our picture. So I'll show you both. So we start with our domain of the parametric equations, which was t was between infinity and negative infinity. And then we take this, when we solve for t, we plug that in right here. So t was y minus 6. Add 6 to all three parts of our inequality, and we still get that y is anything from negative infinity to positive infinity. Okay, so for what values of the curve, for what values of y is the curve defined? For any y value. The other way we could do this is by looking at our picture and figuring out graphically. This is asking us what values of y is the curve defined. We can see that as we move here, we'll hit all of our negative y values. Here we'll hit all of our positive y values. So it's going to be anything from negative infinity to positive infinity. Again, it doesn't use the term domain because that only refers to functions. Any questions on this? Okay, one last one. And this last one is really exciting. It combines together parametric equations, trigonometric functions, and conic sections. All right, so let's graph x is equal to 5 cosine of t, y is equal to 7 sine of t, and t is between 0 and 2 pi. Now, for the sake of time today, I'm going to just tell you the chart of values. You can check this later by hand, or you can check it with a calculator later, but I don't want to go through every single one of these calculations. So what I want to do, if they're asking for t going from 0 to 2 pi, I'm just going to put in some values here. And I think that most of you guys like working with degrees better than radians, so it doesn't matter, right? This is just a middle step. So I'm going to just write some values between 0 and 360 in degrees. So we'll do 0, 30, 45, 60, 90, 120, 135, 150, 180. Then by the time we get to 180, we're going to see the pattern. So I'll put dot, dot, dot. We'll jump to 270, our next quadrantal, and then we'll jump to 360, which is 2 pi. So we'll see the pattern here. Okay, so again, I'm going to give you these chart of values. I'm not going to do them all out by hand. If you want to check them later, you certainly can. Well, maybe we'll just do the quadrantals by hand. I think that's good practice. Okay, so let's check our quadrantals, which are 0, 90, 180, and 360. So we'll draw a little picture here. We know our quadrantal angles, the shortcut is to look at a point that's a distance of 1 away from the origin. So this point is 1, 0. This is 0, 1, negative 1, 0, and 0, negative 1. All right, so first up, x is 5 times cosine of 0. So at 0, cosine is 1. So I have 5 times 1, which is 5. Y is 7 times sine of 0. So when t is 0, sine of 0 is 0. So I have 7 times 0, which is 0. Let's do the next quadrantal angle, 90. So at 90, cosine is 0 and sine is 1. So we have 0, 7. Our next quadrantal angle, 180. Cosine is negative 1 and sine is 0. So we have negative 5, 0. At 270, here's cosine sine. So I get 0, negative 7. And then back to 360, I get 5, 0. Now, maybe from these points alone, you can guess what this shape is. As I already mentioned, it's kind of an exciting example that combines together trigonometry, plane curves, and conic sections. Okay, so think about what these points look like. For the sake of time, like I said, I'm not going to fill these all out, but I want you to be convinced of the shape. So I'll throw some of these values in here just so you can see what it looks like. And these are all angles we could actually do by hand if we wanted to. All right, so now let's put all of these values, and I'll just do the quadrantal ones, and then I'll use the other points to convince you that that shape is correct. So let's put those quadrantal angles on. Again, what we're doing is we're only plotting x and y. We're not actually plotting this angle t. We're using these points to come up with our plane curve. So let me zoom out a little bit so I got some more space here. Oh man, I didn't do a good job of putting that 5 to scale here. Let me put this out here. Let me cross this off. Okay, so we had a point at 5, 0. Then that next quadrantal angle gave us 0, 7. Then we had negative 5, 0 and 0, negative 7. If we look in this first quadrant, the way our points follow is kind of this arc, right? If we were to plot these points, and then they continue out down here. And we get an ellipse. We'll come up with a rectangular equation in just a second as well. One of the other interesting things about this is that the way that this is defined, this t between 0 and 2 pi, this gives us the entire ellipse graphed from 0 to 2 pi, right? We started here and our movement was in this direction. Now, if for example, we had only been given the domain that t was between 0 and say just pi or 180, we would only get from 0 to 180 of the ellipse. We'd only get that portion. Okay, so having this parameterization and having this third variable t, we can actually just graph certain parts of the ellipse if we're only concerned with certain angle measurements in there. All right, so let's come up with a rectangular equation. We already know what the rectangular equation of an ellipse is, so we can actually just write this by hand from looking at the picture, but I'm going to do this algebraically and we'll make sure that it matches up with what we have by hand. Okay, so the trick here is to use the Pythagorean identity. And it is a trick. I don't think it's super obvious. But we know that x is 5 cosine of t and y is 7 sine of t. So my trick is to start with sine squared of t plus cosine squared of t is equal to 1. This is the Pythagorean identity. Then I'm going to take my two equations. So I had x is equal to 5 cosine of t. So solving for cosine of t, I get x over 5 is equal to cosine of t. And we had y was equal to 7 sine of t. So solving for sine of t, divide both sides by 7, I get y over 7 is equal to sine of t. Okay, what I'm going to do is I'm going to plug y over 7 in for sine of t here, and I'll plug x over 5 in for cosine of t here. So sine of t is y over 7. So I have y over 7 squared plus cosine of t is x over 5. So x over 5 squared is equal to 1. Let me label this rectangular equation. The last thing we'd want to do is just get this into our standard form of the equation of ellipse. We always put the x first and we square these out. So I'm going to write this as x squared over 25 plus y squared over 49 is equal to 1. So this is the equation of an ellipse, right? We have a plus in the middle. That's what determines it's an ellipse, not a hyperbola. The major axis is on the y-axis because this number is bigger. The distance from our center out to our vertices is the square root of 49, which is 7, so that looks perfect. And from our center to the points of intersection with the minor axis is square root of 25, which is 5. Okay, so you can either go through this algebraically, or if you wanted to look at this equation and note that the center was 0, 0, A was 7, B is 5, you could have come up with this from the picture.